To begin talking about partial fractions, I'm going to give you an interesting factoid about the fraction 1/12. This fraction is equal to 1/3 minus 1/4. You can verify this easily by noting that this is 4/12 minus 3/12, which is of course just 1/12. But the very interesting thing about 1/3 and 1/4 is that 12 is equal to 3 times 4. This means that we have split a fraction which has two factors in the denominator into two fractions which appear to only have one fraction in the denominator. As another example, consider 1/15. We can assume that 1/15 is equal to a over 3 plus b over 5. But how would we determine what a and b were? We could multiply both sides of this equation by 15 to get 5a plus 3b on the right, which means that 5a plus 3b simply needs to equal 1. If b were equal to 2, then this would be equal to negative 5 equals 5a, because we subtract 6. And then we get a equals negative 1. So we can rewrite this as 2/5 minus 1/3. And 2/5 minus 1/3, we say, is equal to 1/15. In fact, it is, because, well, you can check that for yourself. But we have just decomposed 1/15 into two other fractions. So this is how you do it with numbers. But if you have linear factors in the denominator, if you have, factors of a quadratic in the denominator, you can still perform this cleverness. We can write this fraction as a over s plus 1 plus b over s plus 3. One fraction for every factor. Now we just need to determine what a and b are. To do that, we'll multiply everything by s plus 1, s plus 3 to get s plus 2 equals a, s plus 3, plus b, s plus 1. Now there are a variety of ways to solve this system of equations. What do you mean system of equations, you ask? If we multiply things out and combine like terms, the right side of this equation becomes a plus b times s, as, bs, plus 3a plus b. And it is a property of algebra that the coefficient of a variable on the left is equal to the coefficient of that same variable on the right. So that means that 1 is equal to a plus b, because 1 is the coefficient of s on the left, and a plus b is the coefficient of s on the right. Similarly, the constants are the same, so 2 is equal to 3a plus b. This means we now have a system of equations in a and b. There is going to be one set of a and b that solves this system of equations. However, there is another way to solve this partial fraction system, sometimes easier than the method of a system of equations. We can also plug in clever s's that get rid of either a or b. Watch this. If we plug in s equals negative 3, then we get negative 3 plus 2 equals, and see, negative 3 plus 3 is 0, so we lose this whole thing, plus b. Now, so we're just off with b on the right side, but negative 3 plus 1 is negative 2. This gives us that negative 1 equals negative 2b, and therefore b is equal to 1/2. And if we plug in s equals negative 1 plus 1 goes to 0, so we lose this. So negative 1 plus 2 on the left becomes 1, and negative 1 plus 3 on the right becomes 2a, so that a becomes 1/2. You can observe that this does in fact satisfy these two systems of equations. So ultimately we find s plus 2 over s plus 1 times s plus 3 is equal to 1/2 times 1 over s plus 1 plus 1/2 1 over s plus 3. And if this were a situation where you wanted to perform the Laplace transform, then from the table, we can Laplace transform this to 1/2 e to the negative t plus 1/2 e to the negative 3t. How exciting! There are a couple other hiccups to partial fractions. These are mainly involved in how you set up your final system of equations. For example, suppose you have the following partial fraction, s squared plus 4s plus 3 over s plus 2 squared times s minus phi. If you have a fraction that looks like this, you have to deal with this repeated factor. In order to deal with the repeated factor, you need to introduce two expressions for that factor. The first expression is a over s plus 2, that's one of them, but the other one is b over s plus 2 squared. So you bring in that second power. And if it was a third power, you'd bring in yet another. But we don't have a third power here, we just have one. And then finally for s minus 5, we of course need c over s minus 5. And then we do the whole multiplying by the denominator thing, and we finish solving for partial fractions. I won't solve for this particular example, but that's how you would do it. The reason this is useful ultimately is because, well, you'll notice according to the table, this right here becomes bt e to the negative 2t, and t e to the negative 2t is a term in some of our over-damped in some of our, I think it's critically damped equations. Our final hiccup involves, you may have guessed, unfactorable quadratic factors, like s squared plus 2s plus 5. What on earth are we to do about those? Step 1, complete the square in the denominator. This quadratic factor, s squared plus 2s plus 5, turns into the factored or completed form s plus 1 squared plus 4. If you see such a form in the denominator, you can represent it in partial fractions with the following form. A times s plus 1 plus b, all over the quadratic factor. So there's s plus 1, which is down here, times a plus b. So this is very interesting. Hopefully this pattern makes a little bit of sense to you, but this is what we would write if we had s plus 1 squared plus 4 in the denominator. We would write a times s plus 1 plus b. So there are two terms, two constants, not just one constant, in the numerator of a quadratic fraction. In contrast, s minus 3 just gets a feeble c on top. We'll finish off by actually solving this partial fractions equation. We'll multiply the denominator to both sides to get, we will get this form of the equation. We can plug in s equals 3 to eliminate all of this and get, on the left side, 24. And on the right side, we have 4 squared over 16 plus 4 equals 20c, which gives us c equals 1.2. This will ease our solving of our system of equations because we'll only have 2 equations instead of 3 for a and b, but let's multiply everything out with laborious pain in order to finish our work here. This enormous monstrosity, as squared blah 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 blah. Anyway, we're going to combine like terms in order to set up our system of equations. But first I'm going to plug in s equals -1 now that we have c to ease our work here a little bit. If we do that, we get -1 minus 4 plus 3, which is like -2 on the left. Excuse me, 0 on the left, I'm just dumb. And on the right, this a term disappears, so we're left with b times s minus 3. And then this -1 cancels out this bit, so we're just left with plus 4c. And then since we plugged in, sorry, I forgot to plug in s equals -1 for this bit, so we get this equals -4b plus 4c equals 0, and because we know that this means that b equals c, that means b also equals 1.2. How wonderful. I don't know why this program is compelled to make all of my numbers unreadable. Stop adjusting my lines! Anyway, we'll combine like terms here to come out with a plus 1.2 for s squared, because c is 1.2, and then a minus 3a plus b plus 2c for the s term, which I'll simplify to 3.6 minus 2a. And then on the right side here, -3a minus 3b plus 5c, but I'm not going to be bothered to plug in b or c because either of these two systems of equations will match to, we have a plus 1.2 equals 1, and 3.6 minus 2a equals 4. Either of these can be solved for a. I'll use this easy one to get that a is equal to -0.2. So if f of s once equaled this insane monstrosity, f of s now simply equals, comparing to this original form of the equation, -0.2 times s plus 1 plus 1.2 over s plus 1 squared plus 2 squared plus 1.2 over s minus 3, which can be Laplace transformed as follows. Sorry, I lost a bunch of videos, but anyway, we split this up into -0.2 s plus 1 over blah 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 plus 1.2 times 1 over blah blah blah. I introduced a 2 in the denominator and numerator because you need that for the Laplace transform, plus 1.2 1 over s minus 3, and of course this transforms into this, and this transforms into 0.6, of course, e to the negative t sine 2t, and this transforms into 1.2 e to the 3t, and we are done. It is a lot of work, that is, it just is, but it's not as bad as trying to set up the crazy differential equations required to solve for the step response of a circuit. We're going to talk about step response and how that plays into things in the following videos.